Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library, and I have a great story to tell you. This time I am inviting you to a long and slow journey to the clouds, to the discovery of our atmosphere. We will explore what floats above our heads, the layers of gases that separate us from the void and the cold of space, and the composition of the air. We will also talk about some aspects of climate, like how clouds form, the different types of clouds, why the wind blows, or why northern lights, aurora borealis, appear sometimes. And we will look at what we know about the history of our atmosphere that makes life possible on our planet. We will follow its formation over billions of years, as we did in other exploration journeys, like the ones in space or to the center of the Earth. We're going to travel, and this time it will be from the surface to space, through less and less dense layers of gas, and we will see how the environment changes along the way. That does give us a lot to discover. But first, I would like to let you know that we have a Patreon page for those of you who wish to and can support this project, get more from it, and listen ad-free on your favorite podcast app. Patreon is a platform that allows you to contribute directly to our work financially. Our least expensive tier is $3.50 per month, but it doesn't mean you will get less. We let people contribute what they wish or can, and everyone gets everything that is on our page, because the world is a better place when the sun shines for everyone. You will gain access to 22 exclusive episodes. We add a new one every month, and you can listen and download all the episodes with and without background sounds. And as a token of gratitude, we offer advance releases to our patrons. We have added links to Patreon, as well as links to different streaming options, which may be better suited for you. You will find them in the description of the episode. But now, before we begin, if you wish to, you may close your eyes and allow yourself to forget about any worries. Assume a comfortable position. Maybe move a bit to settle. Take a long, deep, relaxing breath. And when you exhale, do it slowly and feel your shoulders drop. Release the tension in your neck. Let your face soften and your jaw relax. Make sure your fingers are not clenched and that your legs are relaxed too. And allow the sound of my voice to guide you through this journey. And now, off we go. So our journey begins on the beach, in the sunlight. The temperature is just warm enough. A smooth breeze surrounds us, and as you know, all of this is possible only thanks to the atmosphere. It filters the sun's rays. It regulates the temperature. It keeps just the right pressure around us, and it affects everything we see. Starting with the sky itself. It is blue, or sometimes at sunset, red or yellow. But why these colors in particular? Because in fact, The light emitted by the sun is white. It contains all the colors, and actually sometimes we can see them when there is a rainbow. What makes one kind of visible light different from others is its wavelength, or more accurately, its range of wavelengths. The longest light wavelengths that are visible to us look red, and then as they become shorter, as their frequency increases, they look successively orange, yellow, green, blue, and finally violet, which is the shortest visible one. But the spectrum of light extends beyond what we can see. Just past red lie the longer wavelengths known as infrared, while beyond violet are the shorter wavelengths called ultraviolet or UV. We call colors the portion of light wavelengths that the human eye can perceive, our visible spectrum. But this range is not the same for all living beings. Some species experience a very different slice of light. Certain animals, such as some snakes and frogs, can detect infrared, while many mammals, other than humans, including dogs and cats, are able to perceive wavelengths beyond our range, extending into the ultraviolet. A rainbow appears when small raindrops in the air act like tiny prisms that bend and separate the different colors, the different wavelengths. But given that the sun sends us white light, with all wavelengths from the visible spectrum and more on either side of it, why a blue sky? Because the atmosphere and its molecules of gas affect the light. When the sunlight reaches the planet, much of the spectrum passes straight through the atmosphere, including much of the red, yellow, and green wavelengths that are mixed together and still look nearly white. But blue and violet are shorter waves, and just the right size to hit and bounce off the molecules of gas in the atmosphere. This causes these particular waves to be separated from the rest of the light and to become scattered in every direction. Some of the violet light is absorbed by the upper atmosphere. We will come back to this later. And our eyes are more sensitive to blue. That is the reason why the color blue dominates the sky. Blue waves are separated from the rest of light and scattered multiple times as they cross the atmosphere, which makes every corner of the sky appear blue to our eyes. But this is just because of our visible range of light. If a creature on Earth had a narrower visible spectrum that went, for example, only from red to green, to it, the sky would be white because it couldn't see the blue wavelength. Now, sometimes at sunset, the sky around the sun especially becomes red instead of blue. And this is also due to the atmosphere. When the sun approaches the horizon, its light has to pass through more of the atmosphere due to the angle. The sunlight has to cross more miles of atmosphere to reach our eyes. The region of the sky around the sun turns red or yellow because even more of the blue and violet is scattered to the point where it is no longer visible, and this allows for the red, the orange, and the yellow to reach us. Almost the whole sky can turn red for a moment when there are particles of dust, pollution, or water vapor in the atmosphere, because these reflect and scatter more of the reds. But now, let's begin our ascension that will take us to the frontier of space. And as we slowly begin to rise, let's take a look at the composition of the air before we reach the first clouds. As you know, there are two main components to this mix of gas around us that we call air. The main one is nitrogen, which accounts for more than 75% of Earth's atmosphere. And the second one is oxygen, a bit more than 20%. The rest includes a small percentage of other gases like argon and carbon dioxide, and also water vapor. But the composition varies depending on the altitude and the places around Earth. For example, in humid and hot air masses close to the surface around the equator, water vapor can represent up to 5% of the atmosphere in regions where we can feel the humidity in the air, whereas there are just traces of water in cold and dry regions. But as you know, the density of the atmosphere decreases with altitude, and different names have been given to various layers. We are going to explore especially 4 of them, the closest to the ground. The one in which we live is the Troposphere, which extends up to 7 miles or 10 kilometers above our heads, at least when we are at sea level. But none of these layers are uniform. Their density, air pressure, and temperature all vary. We will see that there are exceptions for temperatures, but overall, in general, they tend to decrease with altitude. Within these layers, conditions can change dramatically. For example, even the highest mountains in the world lie entirely within the troposphere. Yet at their summits, the air is thin, making it hard to breathe, and the cold is extreme. Even at the summit of Mount Everest, there are still about 2 kilometers of troposphere above you. Yet the extreme cold and the thin, oxygen-poor air make it necessary to use breathing equipment. Commercial aircraft typically have a cruising altitude of 10 kilometers, 7 miles, just at the upper limit of the troposphere. And they require heating and pressurization. Above 7 miles begins the Stratosphere, then the Mesosphere, and the Thermosphere. But we will come back to that. Above the Thermosphere, the atmosphere has no clear limit. Its density progressively vanishes in a large region called the exosphere, where we will end our journey. But we are going to spend time in the troposphere, because this is where most clouds are located and where most weather patterns appear. As we keep rising, just 1 mile above the surface, we are approaching a first low-level cloud, a stratus. Depending on their form and altitude, there are various different families of clouds, which are called genus, and then many different subtypes that are called species. Under the common term cloud, we name objects with very different shapes and altitudes. They compose a moving picture in the sky that changes constantly. And of course, they drew mankind's attention long before their nature was understood. To our ancestors, far away in the past, it was obvious that clouds were located somewhere between the ground and the sun or the moon, and they were part of mysterious weather phenomena that were often read as signs from higher powers. The first document that we know of that attempted to gather all the knowledge or all the assumptions of the time about weather and climate is a work by a Greek philosopher, Aristotle, called Meteorologica. In it, precipitation like rain or snow and the clouds from which precipitation fell were called meteors, from the Greek word meteoros, which means high in the sky. The modern term meteorology comes from it. Meteorologica was not a scientific work in the modern sense of the term because there was no close observation nor experimentation to validate its content. It was mainly based on intuitions and observations from the ground. But some of these intuitions were quite good. It described for the first time the hydrological cycle, how water moves in different ways, rising from humid regions, forming clouds, traveling through the sky, and eventually falling back to earth elsewhere. Aristotle was a proponent of the theory of the four elements to explain what matter was made of. And in this classification, clouds were obviously water, even though he could not precisely explain why water could remain in suspension in the air. His guess was that the sun sucked fumes out of earth in wet places like rivers or the seas. This would form wet materials, clouds, whereas in dry places, the sun's action would create so-called dry materials like wind. Under comets or shooting stars, and even the Milky Way, which was not understood as a collection of stars like the sun. But until the 19th century, the exact nature of clouds and their formation process remained very mysterious. They were taken as a fact of nature, like the sun or the sky, and they were given a lot of aesthetical or sacred value. In the European Middle Ages, for example, clouds were also considered like mystical swarms that hid heavens from mortals, like a veil of God. The first systematic classification of clouds began in the 19th century, and since then, with the development of observation methods like balloons and later planes, they have been understood better and better as the science of meteorology emerged. So how do clouds form? I told you before that the air contained a percentage of invisible water vapor, which varied depending on the regions of the globe. When the air becomes saturated in water vapor and cannot take more, water vapor condenses to form tiny drops that are light enough to stay in suspension in the air. Sometimes this phenomenon occurs near the ground, producing mist or fog, but it more often takes place at higher altitudes, since the air's saturation point depends strongly on temperature. The colder the air, the less water vapor it can hold before reaching saturation. So when a mass of air rises higher and higher above the ground, it becomes likely to reach its saturation point, its saturation temperature, and form a cloud, because water vapor exposed to a lower temperature will condense into droplets. The temperature at which it happens is called dew point, dW, and this dew point, this condensation temperature, depends a lot on the quantity of water vapor in the air. Sometimes it can be as high as the ambient temperature when there is a lot of water in the air because an adjacent source of moisture saturates it, like a body of water, or transpiration from plants that reject water. And this is how our ground clouds, like fog, appear in wet regions. There is this notion that clouds appear above the sea due to water evaporation. This happens, but clouds can also form above and from land masses. As long as air becomes saturated in water when it rises. But why does air rise higher in the atmosphere instead of staying where it is? There are various mechanisms behind it. The first one is convection. Air near the surface tends to move upwards due to solar heating. During daytime, solar energy hits the surface. Air near the surface becomes warmer, and this makes it travel upwards. This difference in air temperature is what makes flying balloons, hot air balloons, rise. They contain heated air that becomes lighter than the air around it, lifting the whole balloon in the sky. This convective movement due to the sun happens all the time. Another factor that can lift air is a physical barrier. When wind circulation forces an air mass from a low elevation to a higher elevation as it moves over rising terrain, like a mountain chain, and we will talk about wind later. So due to the rising ground elevation, the air is exposed to a colder temperature. The third mechanism that lifts air is frontal and cyclonic lift. There are differences in pressure inside the atmosphere due to effects from the wind in the upper levels of the atmosphere. A region may appear where the air pressure is lower than that of surrounding locations. This makes air masses move, sometimes violently, and these differences in air pressure are responsible for the most violent weather events. It also lifts air masses and contributes to the formation of clouds. Depending on their formation process, their altitude, and their environment, clouds appear in a variety of shapes and sizes. Inside the cloud, it is like a dense mist. But there are not just drops of water in suspension. There are also tiny particles of dust, light enough to be lifted several miles above the surface, around which water vapor tends to condense. So let's explore some of the main shapes of clouds. There are stratiform clouds. These are the most peaceful ones. They appear in relatively stable air mass conditions, and they are generally flat with a sheet-like structure. These are the equivalent to a blanket of fog floating above the surface, and they can be found at every level of the troposphere. At high altitude in the troposphere, that is to say around 10 kilometers or 7 miles high, cirriform clouds may also happen. These have the appearance of filaments, but like stratiform clouds, they are flat because they are not exposed to a strong convective movement that would make them gain height. The third type, when there is a bit of convection that makes them grow vertically, are cumuliform. Cumulus clouds are typically how we would draw a cloud, with a puffy shape and a bit of vertical extent. But these cumuliform clouds may be much bigger and subject to a spectacular vertical rise when highly unstable air stretches them upwards. In this case, they become cumulonimbus. They are the product of very strong convection that can extend up to the lower layers of the stratosphere, and their presence indicates air mass instability. For airline pilots, they typically indicate zones of turbulence that they might want to avoid, if not for security reasons, at least for the comfort of their passengers. These different shapes are just archetypes that have been named to describe clouds, but there are many intermediate possibilities. Their sizes vary, and a cloud or a formation of clouds, when they gather, can have characteristics from different forms. Their structure is not always homogeneous. Depending on the altitude and temperature, water may be more or less dense, and under the form of droplets or tiny ice crystals. Their colors also vary because of their density. As you know, white clouds in a blue sky indicate peaceful, mild weather, at least in the short term, whereas a darker shade of gray is often a sign of impending bad weather, or at least precipitation. This is due to the density of droplets and ice crystals in the cloud. The thicker it gets, the more light it scatters or blocks, which results in less light penetrating all the way through it, resulting in a darker shade for observers on the ground. The particles on the underside of a rain cloud receive very little light to scatter toward our eyes, so the base of the cloud appears gray. But the same cloud seen from above could be very white. At some point, as the droplets grow larger and more numerous, they become too heavy to remain suspended and begin to fall. This is precipitation. Depending on the temperature and the altitude from which they fall, it can reach the ground as rain, snow, or even hail. Clouds are also responsible for lightning and for the sound of thunder that accompanies it. So what is this about? As you know, lightning is a bolt of electricity, and the conditions for its appearance are created in storm clouds, in this large vertical cumulonimbus I mentioned before. Within a cloud, often several miles tall, there can be large differences in temperature between its base and its top. These differences generate powerful movements of air masses both vertically and horizontally. The movement of all these particles, water droplets and dust, rising and falling within the cloud, creates friction, collisions, and exchanges of electrons between them. After a while, zones with different electric potential appear within the cloud. Some parts have a surplus of electrons, others a deficit. Generally, the base of the cloud ends up with a negative electric potential. The coexistence of these regions of the cloud with different potentials creates an electric field, a tension, and once past a breaking point, this accumulated tension is released in a discharge, the lightning, which is a sudden flow of electrons, a bridge between 2 points with opposite electric potential. Depending on the circumstances, it can be from the base of the cloud to the ground, the most frequent case, but also from the ground to the cloud, or between and within clouds. Lightning is not always connected to the surface. So the electric bolt rebalances electric potential, and doing so in a very fast movement of electrons. It generates a lot of heat in a fraction of a second. This is where thunder comes from. The air is suddenly heated by the lightning bolt, so it expands very rapidly, and doing so it creates a shock wave of sound. Typically, we see the lightning before we hear the sound of thunder, because light travels much faster than sound. But sometimes we may hear thunder without seeing lightning. Lightning happened, this is sure, because it is the source of thunder. But it may have taken place out of sight, hidden by the terrain or just above our heads within the clouds. As we keep rising, we will see other types of clouds above the troposphere, but we are now reaching its upper limit, 7 miles above ground, and we are about to enter the stratosphere. Before we examine this new layer, let's take a look at the formation history of our atmosphere. Because if we were to travel hundreds of millions of years into the past, we would not even recognize it. Paleoclimatology is a science that studies past climates when direct measurements could not be taken, and it is closely related to the study of the atmosphere in the past, which can be deduced from what we know of the history of Earth. From atmosphere formation models and all the traces this past atmosphere has left in our soils, from ancient layers of ice to geological layers that can be dated. The formation of our atmosphere has been a long process, and it keeps changing. The earliest atmosphere, when Earth was still a protoplanet in the solar nebula, was probably made of hydrogen, the most abundant element in the cosmos, and a few common compounds like methane, ammonia, or water vapor. We suppose it because these are the ones found in the gas giants like Jupiter or Saturn, and they were as abundant in the early stages of the formation of the solar system as they are now. Of course, no form of life is believed to have ever inhabited the planet in those early times, several billion years ago. But as soon as Earth formed as a planet, it is believed it had an atmosphere due to gravitation that retains a thin layer of gas around the planet. Other reasons to believe it had an early atmosphere are the distance to the Sun. The Earth is relatively far from it compared with other planets, and the appearance of the magnetic field that shielded it from the solar wind that could have carried away its gases. It is common for planets of the solar system and even large, rocky bodies like satellites to have an atmosphere. Sometimes it is so faint, so light, that there is barely anything, just a very scant presence of gases. This is the case for Mercury, which is so close to the Sun that any atmosphere was carried away by a solar wind long ago. Solar wind is this flow of particles that the Sun emits in every direction. The Moon also barely has an atmosphere because it is not massive enough to retain one. On the other end of the spectrum, Venus has a much denser and thicker atmosphere than Earth, one that makes the planet very inhospitable at its surface, with close to no sunlight and super high pressure and temperature. Quite early in the history of Earth, a few 100 million years, this atmosphere was replaced by a new one, a second atmosphere that formed around 3,800,000,000 years ago. The second atmosphere appeared in the late formation of the solar system, when planets like Earth received the heavy bombardment of huge asteroids. Volcanism was intense, releasing gas in the atmosphere that was supplemented by what asteroids brought, and a new layer of mainly nitrogen plus carbon dioxide and a few other gases replaced the early ones. This was the first major step towards the formation of our atmosphere, where nitrogen dominates, but at the time there was close to no oxygen yet. Thanks to a relatively warm climate, there was liquid water on the surface, and this is the environment where it is believed that early life appeared, initially in the form of bacteria. These bacteria lived on photosynthesis. They used solar energy to fix carbon from carbon dioxide and reject oxygen as a byproduct of their feeding and energetic cycle. But it took a lot of time before this oxygen was released freely into the atmosphere, because for hundreds of millions of years, this oxygen was consumed by oxidation of various materials, notably iron. Once the production of free oxygen exceeded the availability of reducing materials that removed it, oxygen began to accumulate into the atmosphere. At the start, it was traces. Then it rose to a few percentage points, and it reached the kind of rate we have today, that is to say, around 20% of the atmosphere composition about 300 to 400 million years ago, with large fluctuations over time. This new age for the atmosphere, the age of oxygen available freely, is called the third atmosphere. And it is during this one that larger terrestrial life forms appeared. There were times when the oxygen content of the air was significantly higher than it is today, up to 30 or 35%, 300 million years ago. It is believed that this contributed to the emergence of species of very large insects that could breathe in such an oxygen-rich environment, whereas they would be unable to survive in our current atmosphere. In any case, the percentage of oxygen has varied between 15 and 30% for the past 500 million years, and the exact causes of this brutal variation are not exactly known. They are brutal on a geological scale, but they still happened over millions of years. So, of course, they were imperceptible to living creatures at the time. Planet activity that consumes carbon dioxide to release oxygen is certainly a factor in these variations, but so is probably volcanism that can release gases that are oxygen hungry into the atmosphere, such as sulfur. The most notable evolution of the atmospheric composition over the past 200 years is a fast rise in the carbon dioxide rate, which comes from human activity, especially the use of fossil fuels. Now, if you look at the figures, carbon dioxide is a very small part of the air we breathe. On average, it accounts for 0.04% of the atmosphere. It looks quite negligible, but this rate has risen steadily since the beginning of the 20th century, about 100 times faster than at any point measured in the past 1 million years. Along with other greenhouse gases, those that trap heat in the atmosphere, carbon dioxide is considered a major contributor to the rise in average global temperatures observed over recent decades. Because even in very small quantities, it can have a visible impact on average temperatures. These rates of carbon dioxide are associated with higher temperatures that existed over the past 1 million years, but they came with significantly higher sea levels due to less ice being stored and different weather patterns too. Hence the efforts to limit or reduce emissions around the world. If we take a look at the climate history of our planet, dramatic shifts in temperature and the composition of the atmosphere are a constant feature, but they happened over long periods of time, and we know that they deeply affected life, favoring the emergence of new species and condemning others to decline or relocate to other regions. But let's resume our journey. We are now entering the stratosphere, second major layer of Earth's atmosphere above the troposphere that we just crossed. Its altitude varies depending on where we are on Earth. Near the equator, it begins as high as 12 miles or 20 kilometers above our heads. At the poles, about 4.5 miles. And in between both Europe and North America, around 6 to 7 miles. A notable feature of the stratosphere is that, contrary to the troposphere, its temperature rises with altitude. At the frontier between the two, the temperature is typically minus 60 degrees Fahrenheit or minus 50 degrees Celsius. This is the temperature outside a commercial aircraft at cruising altitude. These temperatures we could not bear. and they are exceptional on the Earth's surface. 40 to 50 kilometers higher, where the stratosphere ends, the temperature has risen to 50 degrees Fahrenheit. Why this rise in temperature, which is not very intuitive, because the more you go up from the ground, the closer you are to the cold of space. The reason for this is the ozone layer. Ozone is a form of oxygen, but instead of the usual molecule O2, it has 3 atoms, O3. Oxygen naturally prefers to exist as O2, which is more stable. Ozone, on the other hand, is less stable and tends to break apart into an O2 molecule and a single oxygen atom. But ozone appears in the stratosphere because solar radiation, especially in the ultraviolet frequency that we talked about at the beginning, UV rays, separates molecules of O2 into 2 free atoms. These atoms combine with another molecule of dioxygen to form ozone, which itself absorbs other radiation on different wavelengths and splits again into O2 and the free atom of oxygen, and the cycle goes on. In this process, most incoming solar ultraviolet radiation, about 97%, is absorbed. And this is why the ozone layer is a shield that stops most of this radiation from reaching us, from reaching the surface. The whole process with dioxygen molecules splitting, ozone appearing and then splitting again, this generates heat. And this is the reason why the more you rise into the stratosphere, the higher the temperature becomes. Beyond the stratosphere, in the Mesosphere, that we will reach in a moment, the temperature decreases again with altitude. Another difference of the lower Troposphere is the absence of vertical convection movements. In the Troposphere, air masses that are warmer tend to be located below the colder layers, hence the convective movement that makes warmer air rise. In the stratosphere, it is the other way around, and the differences in temperature, taking into account the distances, are not as important. So overall, the stratosphere is free of convective activity, which is a cause for turbulent weather in the troposphere under it. Speaking of which, let's take a look at winds. Why and how do they blow? Wind is the movement of air from regions of higher pressure to regions of lower pressure. This occurs because solar energy is unevenly distributed across the surface of the planet. There is a constant temperature difference between the poles and the equator, which receives more heat. At any given moment, there are differences in temperatures between various points of the globe, and the difference in temperature means a difference in pressure. Hotter air tends to expand, whereas it contracts when it receives less energy, less heat. The flows of air are a mechanism that constantly tries to rebalance these differences in pressure. At the scale of the planet, there are large flows of atmospheric circulation between the equator and the poles. And on the local level, there can be many particular movements, always due to differences of temperature and pressure between 2 points. And these ones can be responsible for a smooth breeze or a tornado under a storm. Another factor that affects wind is the spinning of Earth. The atmosphere is not independent from the planet. It is bound to it by gravitation, so it spins with it, and luckily for us, because Earth spins at more than 1,000 miles per hour. So if the atmosphere didn't move with it, we would be exposed to the sensation of a wind traveling at 1,000 miles per hour that would rip everything off the surface. But the spinning of the planet creates a force called the Coriolis force that deflects winds. In the northern hemisphere, it tends to deflect them to the right, and in the southern hemisphere to the left. The Coriolis force is proportional to the rotation rate of a plane of reference. What does this mean? In this case, the planet is the plane of reference, and it spins on its axis in 1 day. At our scale, this is relatively slow, so the Coriolis effect is not visible in everyday life, but it determines the rotation of larger phenomena like cyclones. The cyclone is a large air mass that rotates around the center of low atmospheric pressure. It becomes visible, especially from space, thanks to the clouds that follow the direction of the flow. There is a popular theory that the Coriolis force also determines the rotation of draining water in a bathtub. When you empty it, there is often a rotation, a tiny whirlpool of water around the hole. It says that the water rotates clockwise in the southern hemisphere and in the opposite direction in the north. But this is just a legend, which has been disproved by experimentation. The Coriolis force is too small at this scale, and there are many other influences on the rotation, like just the surface of the bathtub or movement in the water when it begins to drain. These influences are much stronger than the Coriolis effect in this case. We are now reaching the upper part of the stratosphere. We have passed through the ozone layer, and we are going to enter a new main layer, the third one, the Mesosphere. We are not in space yet, but it becomes clear that we are approaching it this time. Temperature decreases again with altitude, and over the 50 to 60 kilometers of the Mesosphere, it falls from minus 15 degrees Celsius, minus 100, or minus 150 degrees Fahrenheit. Apart from the cold, the other thing that makes the Mesosphere inhospitable is the thinness of air. We couldn't breathe, even less, in the stratosphere, and as a result, the low pressure due to the rarity of air, aircraft cannot reach it. Only the lowest few kilometers are accessible to balloons. For balloons, the altitude record is 53 kilometers. Only rockets or space shuttles have crossed the Mesosphere on their way to space, and measurements have been made with sounding rockets that could collect information for a few miles per mission. So the Mesosphere is more mysterious than the Troposphere and Stratosphere, but not devoid of phenomena that sometimes remain unexplained. One of them is electrical discharges or lightning that have been observed within the lower Mesosphere and are the subject of current studies. Another feature of the Mesosphere is noctilucent clouds, or night-shining clouds, which are the highest clouds in Earth's atmosphere at altitudes of 75 to 85 kilometers, about 50 miles. They are too faint and distant to be seen in daylight from the ground, and appear only for a short time at twilight. We know that they are composed of tiny crystals of water ice, but the source of the material they are made of in the Mesosphere is not known with certainty. Let's continue our journey up, because we are now leaving the Mesosphere and entering an even more inhospitable layer, and by far the largest we have crossed so far, the Thermosphere. We are still within the atmosphere, but this looks and feels more like space already. The density of air continues to drop down to an almost insignificant level, and objects in low orbit, like the International Space Station, are located inside the Thermosphere. The air is so faint that meteors don't start burning in it. When they approach Earth, they are met with the increasing friction in the Mesosphere under, and typically start burning and disintegrating in the Mesosphere and Stratosphere, where they turn into shooting stars. But a well-known phenomenon takes place well above this in the first third of the Thermosphere. Northern lights, also known as aurora borealis. In fact, the phenomenon can be seen near both poles of the planet. It also happens in the south, where they are called aurora australis. Northern lights indicate that the atmosphere is still present at these altitudes, 150 miles above our heads, because without it, it could not happen. They are the result of an interaction between solar wind, magnetic field of Earth, and particles in the thermosphere. What happens? The sun projects this flow of particles constantly, but its intensity varies, and when solar activity is more intense, the magnetic field of the Earth that shields the planet from it does not entirely deviate the flow. So, some of the electrons and protons carried away in the solar wind enter the upper atmosphere near the poles due to the shape of the magnetic field. Instead of the void space, you arrive in an environment where gases are floating, mainly nitrogen and oxygen, and they collide. They shake up these elements, which release energy in the form of light. Different types of particles in the atmosphere make different colors. They have a different signature. Oxygen makes green and red light. Nitrogen makes blue. We generally see northern lights as green because the green color produced by oxygen is the brightest, and our eyes see it better. The solar wind that has entered the upper atmosphere creates what appears as draperies of light that float high in the sky and are a reminder of the protection that the magnetic field and the atmosphere bring to the planet. Beyond the thermosphere, more than 400 miles above us, the density of gas is so low that the atmosphere nearly ends. Only a few atoms and molecules of hydrogen and helium remain. They are so far apart that they can travel hundreds of miles without colliding with one another. This last layer, where the atmosphere disappears, which can be considered as space, extends up to about 10,000 kilometers or 6,000 miles. This is where most of the satellites orbiting Earth are located. And at these distances, the effects of the magnetic field decreases enough for these few remaining particles to merge with solar wind. This is also where we reach the end of our journey for tonight. I hope you enjoyed this journey through Earth's atmosphere. There are more of these stories about science available if you are interested, from the infinitely small to the immense expanse of space, and you can find them in my library. But for now, you can drift. Let yourself go to a restful sleep. And until we meet again, good night. Sleep well.